Okay, so with the power of the two-photon microscope, this mode locked laser firing out these ultra high but tiny short pulses of infrared light, we can now image in the brain. With the power of genetically encoded calcium indicators, we can get whatever cell we want to express the the sensor, the GCAM. So what, right? What good is it getting it in the animal if the animal is, you know, you have to chop the animal's head off. You might as well have just gone back and done it in a slice, right? Can we do this in vivo? Can we not just do it in vivo, but in an awake behaving animal? Yes, we can. So, um, most of this work so far has been in that I've presented to you has been in anesthetized mice or rats. So then there was the invention of the chronic cranial window, which I think you got talked about a little bit, right? So basically, a small hole is cut in the skull with a variety of different techniques, and then a piece of glass, a microscope slide essentially, is put over that hole, and then with various glues and tricks, um, you seal it down, and now you have an image, a window into the brain that you can do your two-photon microscopy through. There's another approach called a thinned bone window, where essentially you very carefully shave away the bone as thin as possible, but without breaking it, and you can image through that too. Arguably, this is a better that is a better technique. It's also harder and less popular. So anyway, the point is that after 10 weeks, you can still see through this cranial window basically just as well, with no sign of infection, so long as you do the surgery right. Um, then you combine that with the so-called head fixed preparation. So mice can be trained to accept head fixation relatively easily. So basically, a small piece of metal of various different shapes and sizes is glued to the mouse's skull, and then that piece of metal can then be fixed underneath the microscope. Now, the mice don't like it to begin with, but they can be trained that it's not actually that bad. You get some rewards here, and they'll learn to accept it relatively easily. They'll be going to sleep, underneath the microscope, which actually can be a big pain in your experiments. Um, and you can get the mouse to do all sorts of things. Typical things are um, like a go no go trial. So you show the mouse two stimuli. And if they respond in some way to one stimuli, they get a reward, and if they respond to the other stimuli, they get nothing. And so they should go in a certain case and no go in another case. Again, this should be reminiscent of CHP 311. So this is pretty good, and a lot of science is done like this. But can we do even better than that? So we can kind of. So this is a Miniscope. I have one just in a little box, just up there. So this is a head-mounted, not two-photon microscope. It does not take the world's best image. Basically, the same kind of CMOS sensor that is in your phone. Um, CMOS just is to do with the technology that they make it with, right? But it's basically a phone camera can be mounted on a little chip. They can use a bright LED as the excitation source. They use the dichroic mirror that you've already learned about to split the light, and then they can take an image. And doing this, you can get calcium signals, which is shown here. Now, the at the edge of the image, the focus breaks down, but in the middle, you're away. Um, These are vary. If you can get really quite cheap ones for just a couple of $1,000s, or you can pay tens of thousands of dollars for sort of the creme de la creme ones, and they get some use. They have pros and cons, like everything, but the ability for the mouse to move freely. Uh, Now they're even wireless ones. So here we see the cable that sends the image data back to the computer, but now it comes in a wireless version. So the ability to have the mouse essentially move freely while you can record neural activity is pretty useful. Now, even further, we now have head-mounted two-photon microscopes. These have not received wide pickup, as far as I'm aware. They've not received wide usage. Incredibly impressive technology. Again, using the technology that we developed for um, cell phones. So they use a MEMS scanning method. So MEMS is the same technology that it creates the accelerometer signals in your cell phone, but it basically means that it's a tiny micro machine. Um, and so the light source has to come from somewhere else. The infrared laser has to come from somewhere else. But basically, the scanning and the focusing is done in what is mounted on the head. Finally, just while we're talking about sort of more recent uh, techniques, um, so the two photon cranial window approach is great for the cortex. Really, just the superficial layers of the cortex. Layer 2, 3, you're good. You know, you can start to go deep in that and it starts to break down. Now, there are these special optical components called grin lenses, which are what are used in the Miniscope, which allow you to image deeper, but they are a millimeter or two across. In order to insert them into the brain, you need to remove a lot of tissue. It's a pain. You don't get great images. Um, So not a lot. They get used, but not a lot. So there's one final thing called fiber photometry, where essentially a an optical fiber, so a glass fiber, like fiber optics, is inserted into the brain, and it's inserted into an area where there are GCamp expressing neurons, and then basically the same thing. Light is sent down the fiber. This excites some um, light, sorry, some fluorescence. They emit the light that comes back through the fiber, and this is detected. But because of this, there is no spatial information, right? It's just you just get one brightness signal. So you can't tell whether it's one neuron or 100 neurons. However, it is very good because of the fact that it's just the mouse is only tethered by this fiber and allowing the mouse to freely move. Um, it has some other problems to do with the fact that when the optic fiber bends, the amount of light that go through it changes a lot, and this is a much, much bigger change than the change that is due to the calcium signal. So there's a variety of techniques that are needed to deal with this, um, but this definitely gets quite a lot of use, especially in these sort of neuromodulatory systems. That is to say, you know, people don't really think, or a lot of models about things like dopamine or serotonin, they just model it as sort of one neural population that does just fires more or less. And so if all you're caring about is whether the neurons fire more or less, this is perfect, right? You don't care if neuron A fires a lot, then neuron B fires a lot, right? You just measure that as one constant firing a lot, even though maybe different neurons are doing slightly different things. And so that works perfectly for this.